For this FRQ, we have some data on a gasoline storage tank filled by a pipeline from a refinery. And gasoline flows from the tank into trucks that will make deliveries to gas stations. And the amount of gasoline is given by the twice differentiable function g. T is in hours, 0 is less than or equal to t is less than or equal to 10. And the table gives us t and g of t, and it is known that second derivative is greater than 0 for 5 to 10. All right. Read it really fast because you guys could have read it yourselves and probably already did. Okay, so first we use the data in the table to estimate the rate of change of the amount of gasoline in the storage tank at time t equals 3. So since 3 is right between 1 and 5, we know that g prime of 3 will be approximately the average rate of change between 1 and 5. So g of 5 minus g of 1 over 5 minus 1, which is 19.5 minus 18.5 over 4, which is 1/4. So the rate of change in the storage tank at t equals 3 is about 0.25. And it's in thousands of gallons. So the rate of change will be 0.25 thousands of gallons or 1,000 gallons per hour. For part B, we're looking for, is there a time t where g is increasing at a rate of 0.2 thousand gallons per hour? So essentially, since g is, I'll write it, since g is twice differentiable, because it tells us, g is differentiable, therefore g is continuous. Since g is continuous, we can use the mean value theorem, or MVT. So we'll look at the average rate of change from 0 to 10. So we'll look at these 2 points from the table. So the average rate of change will be g of 10 minus g of 0 over 10 minus 0, which is 24 minus 22 over 10, which is 2 over 10, or 0.2. And we're looking at, is there a time at which g of t is increasing at a rate of 0.2 thousand gallons per hour? And essentially, by MVT, since the average rate of change is 0.2 thousand gallons per hour, from 0 to 10, g prime of t must be 0.2 at some time t. Part C. We know that g prime of 5 is 0.5, so apparently we'll use that somewhere. We use the locally linear approximation for g at time t equals 5. We want to approximate how much is in the storage tank at t equals 7. And then we'll talk about whether it's an overestimate or an underestimate. Okay, so basically we're looking at accumulation. So g of 7 will be approximately equal to g of 5 plus the integral of g prime of t from 5 to 7. So g of 7 is approximately, well, g of 5, 19.5, plus, and we're using our approximation at time t equals 5, so we'll have the integral from 5 to 7, and instead of g prime of t as our slope, we're using 0.5 from here in the problem, dt. So now g of 7 is approximately 19.5 plus the integral of 0.5 is 0.5t from 5 to 7. So g of 7 is approximately 19.5 plus 0.5 times 7 minus 5, or g of 7 is approximately 19.5 plus, well, 7 minus 5 is 2, 0.5 times 2 is 1. So g of 7 is approximately 20.5 thousand gallons. Now we want to look at if it's an underestimate or an overestimate. And this always has to do with concavity. Let's see what else we have. We know that g double prime of t is greater than 0 for 5 to 10, which is what we're looking at, between 5 and 10, or specifically between 5 and 7. So, since second derivative of g is greater than 0 for 5 to 10, g is concave up. And what does that tell us? Well, let's sketch a little picture. Concave up will look like this, kinda. My drawings are bad. And if you look at linear approximation, it's below the actual curve, no matter where you put it. So if it's concave up, I don't know which side, doesn't matter, you'll have an overestimate. So since the second derivative is greater than 0, g is concave up, and g of 7 is an underestimate. Part D. We have the rate at which gasoline flows out of the storage tanks into trucks, given by R of T right here. We want to know when the rate at which gasoline flows out of the storage tank is at an absolute maximum. So first, if this is R of T, we want to find, well, critical points essentially, because we're looking for a maximum value, we need to take the derivative. R prime of T, use some quotient rule, derivative of the numerator is 100, times t squared plus 4 minus derivative of the denominator is 2t times the top, which is 100t, all over the denominator squared, t squared plus 4 squared. And now it's really just simplifying. So we get 100t squared plus 400 minus 2t times 100t is 200t squared divided by t squared plus 4 squared. And we end up with 400. 100t squared minus 200t squared is minus 100t squared, all over t squared plus 4 in parentheses squared. And so for critical points, we're looking for when this is 0 or undefined. The denominator, well, it's squared, and you're always adding 4. So this will always be positive, a positive value plus 4. So this will never equal 0. So we're looking at the numerator. 400 minus 100t squared equals 0. When 400 equals 100t squared, or when 4 equals t squared. So t is 2 or negative 2. But since time is passing, a negative value really doesn't do anything for us. So we'll look at t equals 2. So this is a critical point. Now we really need to test and see if this is actually a point where the derivative changes, or when there's a relative max or relative min. So if we test the derivative at, here's t, here's r prime of t. So at 2, it was 0. Let's test 1 and 3. So r prime of 1, switch colors just because. If we look at this most simplified version, we put a 1 in, the numerator will get 400 minus 100, which is 300, which is positive. Denominator is always positive, so derivative is positive. If we check at 3, denominator is always positive. Numerator at 3 would be 400 minus 900, which is negative. Negative over positive will be negative, so negative. So it looks like 2 will be the location of a maximum. So now, here's what we know. Since r prime of t equals 0 at t equals 2, and the derivative goes from positive to negative, t equals 2 is the location of a relative maximum. But we weren't asked about relative, we were asked about absolute. Well, since t equals 2 is the only critical point, on the interval from 0 to 10, it must also be the absolute maximum, because on either side, the values were decreasing.